All right, everyone. Welcome back for another deep dive.
Yeah. It's excited for this one.
Me too. This one's going to be good. We're going to be looking at electricity and magnetism today.
Two sides of the same coin?
Yeah, kind of, right? So
Good.
to do that, we're going to be using a summary of AP Physics C, electricity and magnetism.
This is like high-level stuff.
Oh, yeah. Yeah. This is, if you were really serious about physics, you're taking AP Physics C.
College level.
So
Yeah.
we're going to break it down. So if you're just curious, like, what is this electricity stuff?
How does my phone work?
Exactly. Stick with us. We'll try to make sense of it.
We'll explain it.
So the very first thing we got to understand is like the foundation of electricity, and that's electric charge,
Yeah.
right? This idea that there's these things, they're positive or negative, and they dictate how electricity is going to work.
It's like the atoms of electricity.
Yeah. Yeah, kind of. And, you know the rule, opposites attract.
Right. Positives and negatives.
If they're the same, they push each other away.
Right. Like charges repel.
So two positive charges. No way. Get away from it.
Magnets, right.
Yeah, exactly. Like magnets.
North and south poles.
Okay, so that's kind of the basic idea. But then we have Coulomb's law, right? Which is basically a way to calculate how strong that attraction or repulsion is going to be.
Yeah. Yeah. It quantifies that relationship. You can think about it as a formula. The bigger the charges, the stronger the force. And the closer they are,
Yeah.
the stronger that attraction or repulsion.
Yeah, so if they're really far apart, like, it's not that big of a deal.
Right. It peters out.
But if they're right next to each other, it's like, woo.
Exactly.
Okay,
Yeah.
so we've got the charges, we kind of know how they interact with each other. Now we got to get into this idea of electric fields, which I always thought were kind of mysterious.
Yeah.
Like, I kind of get it, but I don't get it.
It's like, what is a field?
Yeah.
A field, you can almost think about like an aura,
Okay.
around a charge. So any other charge that enters that aura is going to be influenced by it.
So it's not the force itself, but it's the area where the force can act.
Right. Exactly.
Okay. And I think it makes sense to go to Gauss's law now, because it's like, all right, now we have this electric field. How strong is it?
Right. And this is particularly useful when you have symmetrical situations,
Okay.
like a sphere or a cylinder. It really simplifies those calculations.
So Gauss's law is like helping us figure out how strong is the field in this particular like area.
You got it.
Okay. All right. And then we get to the voltage, which is, some people say it's like electrical height.
Yeah, I like to use the analogy of gravity.
Yeah.
If you lift something higher, it has more potential energy.
Right.
Right. So if you're pushing a charge against an electric field,
Yeah.
you're basically raising its voltage, giving it more potential energy.
Okay. So it's not the actual energy, but it's the potential to do something.
Exactly.
Like make a light bulb light up. Right. And then, so that kind of leads into capacitance.
Right.
Which is this idea that some objects are better at storing that charge than others.
Yeah, I mean, some things are better at holding charge than others, just like some things hold water better than others.
Yeah, so you can think about it as like a really awesome battery or something like
It's
that.
like a supercharged battery almost. Yeah.
Okay, so all right, so we've gotten through charge, we've gotten through fields, we've gotten through the ability to store charge. Now we got to talk about how it moves.
Right.
Current and resistance.
Yeah.
And I think the best way to think about it is like water flowing through pipes.
Yeah, classic analogy.
Right. So current is how much water is flowing.
Uh-huh.
And resistance is like how narrow the pipe is.
Exactly.
So if it's a really wide pipe, tons of water can flow through.
Low resistance.
Yeah, very low resistance.
Smooth sailing.
But if it's a really narrow pipe, it's like,
high resistance.
yeah, it's going to be tough to get through.
Exactly.
Okay, so that's electricity. I think we covered electricity.
Covered it.
Now we're going to flip over to magnetism.
Yeah.
And magnetism, I think, is one of those things, you play with maggots as a kid.
Right.
And you're just like, whoa, how is this working? It's like this invisible force.
It's magic.
It is magic, yeah.
Yeah.
So and the thing about magnetism is it's all about moving electric charges.
Yeah. It's electricity in motion.
Yeah. So we just talked about in electricity, when charges are flowing, that's current.
Right.
So anytime you have a current, you're going to have a magnetic field.
Exactly.
Okay.
And that leads us to the Lorentz force,
Okay.
which is basically a force that acts on a charge as it moves through a magnetic field.
So if I have like a little charged particle and it's moving and then there's a magnetic field, it's not just going to go straight. It's going to get pushed or pulled in some weird direction.
Exactly. It's like a crosswind.
Okay.
You know, if you're running through a field, a crosswind is going to push you sideways.
Okay. All right. So we're talking about like individual particles here,
Right.
but obviously there's like bigger currents and all sorts of things. And to figure all that stuff out, we use these things called Biot-Savart and Ampere's laws.
Yeah, these are like the tools that physicists use to figure out how much magnetic field is produced
Okay.
by different configurations of currents.
So like if we have a wire
Right.
and it's all loopy or whatever, and we know how much current's flowing through it, we can use these laws to be like, okay, what's the magnetic field going to look like?
Right. Exactly.
Okay. All right. Now things get really interesting when we start talking about changing magnetic fields.
Oh, yeah.
Right? Because that's where we get to Faraday's law,
Right.
which is basically saying if you change a magnetic field near a conductor, you're going to induce a current in that conductor.
Right.
So imagine you have like a coil of wire
Uh-huh.
and you move a magnet near it.
Yeah.
Suddenly, you have electricity flowing in that wire.
Just by moving a magnet.
It's crazy,
Huh.
crazy. So that's how generators work.
Yeah.
That's how we make electricity. It's crazy.
Heck, like magic.
It's like magic, yeah. And then to add on to that, we have Lenz's law,
Mm-hmm.
which is basically saying, okay, this current that you induce, it's always going to oppose the change in magnetic field.
Right.
So it's like nature doesn't like change.
It's like inertia, but for magnetic fields.
Yeah. Yeah, it wants to keep things the same, so it's going to push back against whatever change you're trying to make.
Yeah.
And then last but not least, we got to talk about the force on a current carrying wire in a magnetic field. Because this is how motors work.
Yeah.
This is how we take electricity and turn it into motion,
Right.
right? So if you have like a loop of wire
Mm-hmm.
with current flowing through it and it's sitting in a magnetic field, it's going to experience a force that's going to try to rotate it.
Yeah.
And that's how a motor spins.
That's it.
Pretty cool. Pretty cool. All right. So we've covered electricity. We've covered magnetism. Now we need to bring it all together with the grand finale, Maxwell's equations.
The big kahuna.
Yeah, right. Like this is it. This is everything we know about electricity and magnetism summed up in 4 equations.
They basically tell us how electric charges create fields, how those fields interact with each other, and how changes in one field can create changes in the other.
So it's like the unified theory of electromagnetism.
Yeah, pretty much.
And what's really cool is these equations, they actually predicted the existence of electromagnetic waves,
Which is light.
which is light.
That's what light is. It's an electromagnetic wave.
So all this stuff we've been talking about, charges and fields and all that, that's all light is.
It's all connected.
It's all connected, yeah.
Yeah.
That's amazing.
Amazing.
We've gone from like these tiny little particles attracting and repelling each other to understanding like how light works.
It's a pretty big jump.
It's a huge jump.
Yeah.
It's incredible.
Yeah.
All right, so I think we covered a lot of ground today. And I think the biggest takeaway for me is just how interconnected all of this is. Like electricity and magnetism, they're not 2 separate things. They're 2 sides of the same coin.
Right.
And they're responsible for so much of the technology that we use every day.
Yeah. Everything from our phones to our lights to our cars.
It's crazy to think about. So on that note, I'm going to leave you with a question. What other amazing discoveries are waiting to be made in the world of electromagnetism? I'm not sure, but I'm excited to find out.
I'm excited too.
So until next time, keep exploring and keep asking questions.
We'll see you then.
See you later.